The future of radiation sterilization. Sie merken schon, we're going to switch to English right now. This is one due to our speakers who don't speak German, but also to our mixed auditorium. Many of you are English speakers, native speakers. So welcome back. And for all those who are jumping in right now to the Irradiation Service Days 2021. We already outlined some of the potential, but also the challenges of technologies, regulatory frameworks, issues, and the growing market. So I think it appears quite fitting to ask about the future of radiation as a whole, of radiation sterilization, that is, of course, which we will do in a discussion with Florent Kuntz, with Martin Comben, and with Andreas Ostrowicki. So the global demand, we learned today, for single-use medical devices continues to grow at a rapid pace, and multiple technologies are at hand, are available to the industry for sterilization processes and the products. Rapid growth in demand and pressures on key sterilization technologies has resulted in restraints to sterilization capacity today, also covered in other sessions we had today already. Challenges to well-established sterilization technologies are being addressed, and new irradiation technologies are now being commercialized to help meet demand. So the mix of sterilization technologies will change over the coming years, but all technologies will remain critical to meet the demand. To set the stage, we will have opening remarks by Florent and Martin. So we jump right in. Florent Kuntz is with us. He received his physics engineer diploma in the field of nuclear science from University of Strasbourg, France. His involvement in radiation processing began during his PhD works, in which he conducted research on new developments in electron beam dosimetry. Kuntz is working with Ariel, a technological resource center, as project manager in radiation processing and dosimetry. In the field of radiation processing, he performs trainings on industrial irradiation dosimetry, helps the industry in dosimetry system question, selection, and calibration. Kuntz has also developed several famous dosimetry equipments. As dosimetry expert, he conducted several missions with the International Atomic Energy Agency and is a member of ASTM and CN-ISO committees. Method and measures. Florent, opening the remarks by you. Bonjour à Strasbourg, comment ça va?
Bonjour Andreas, merci beaucoup. Thanks a lot for this kind presentation. So I will try to share my screen, which should be this one. Can you hear me clearly?
We do. We can hear you clearly, and we are still waiting for the presentation, but I think this is a question of a few seconds or half a minute or something.
Can you see this? Can you see the presentation now?
I don't think we do right now. Maybe you have a chance to retry to share this. Now something is ticking, Florent. Now we can see, Ariel, the future of radiation sterilization. Wonderful. And now we can see the full screen. Thank you.
Great. So I had some problems to hear you sometimes. I hope that the line will not be cut during this presentation. So it's a general presentation about the technologies used for radiation sterilization, technologies and process control tools. So as you said, I'm with Arial, which is located in this very nice, you see, a very famous picture here, very nice town of Strasbourg, south of Strasbourg. And Arial exists since 35 years. I think it was mentioned already by Andreas. So I go ahead with the techniques and technologies which are involved in our process, jumping directly to the main subject of the presentation. So you may have heard today, and you will still hear tomorrow, that irradiation can be performed with E-beam, with gamma rays, and with X-rays. They all have different advantages and limitations. The separation I do here is about the origin of the radiation. So on the left-hand side, it's machine-sourced radiation, and the right-hand side is the source-based, so cobalt-60. E-beams, X-rays are produced with an electron accelerator. E-beam is a corpuscular radiation with a given mass, a given charge, electrical charge. So obviously, and you can see here, the penetration depth inside the product is limited. However, it is possible to irradiate a lot of products and medical devices with E-beam. It's probably the most efficient way of treating the products, efficient in terms of energy or energetical aspects. X-ray is the conversion of E-beam, of electron beam in a target, very often a tantalum target, to create this X-ray beam, a photon beam, which then has the properties of the gamma rays, which are emitted. They are emitted by a source, a radioactive source. So photon is the interaction of photons with matter is probabilistic, so we can treat palettes of products with X-rays, which makes it very, very interesting. So you could recognize that I did not speak about beta, because beta is, and I dare to say that to BGS, beta is an electron, but which is coming from a radioactive source. So we better speak about electron beam. So what are the components of the irradiation plants? There is somewhere an engine, the emitter of the radiation, so accelerator, source, and of course we have to shield that radiation source with a lot of lead, stainless steel, concrete, etc. And in order to process the products through the radiation field, there is a maze inside this huge concrete building, a maze which can be used to feed in the products and feed out the products after irradiation. And this is the blue line here is the symbol of a conveyor system. Of course, there is a separation door here, which is there for security and safety aspects. So the process today is controlled mainly, not essentially, but mainly with dosimetry. So how is dosimetry important in our application? For each of the medical device, and this is one of the examples you see here on the slide, the producer has to define two dose values. The first one, deep purpose, is this. In the case of this item here, is the sterilization dose. And this is the responsibility of the medical device manufacturer. On the higher side, he also has to define what is the maximum acceptable dose, which can be given to that product, so as to make sure that this product, after irradiation, after sterilization, is still having good properties and not too much impacted by the radiation throughout its life. On the other side, the service contractor has to make sure that during the process, this product is irradiated in a way that the sterilization dose and maximum dose are not, the sterilization dose is exceeded, but the maximum dose is not exceeded. Make sure that the process is running in between the two product dose limits. How is that done? Today, there is several dosimetry systems and dosimeters which are used, mainly optical dosimeters, which turn blue, pink, red, etc., which are single dosimeters, as the pink one, GEX, FWT, the blue one, and the Harwells here for gamma. But there is also films, this role of CTA films. When this film is irradiated, it doesn't change color, so the measurement is done with UV light. And then we have these pellets and blister tape tab packaged alanine dosimeters, which is coming more and more in the industry, because it's probably one of the most, it's for sure the most sensitive dosimeter, and one of the most accurate dosimeter. So today, the process control for our irradiation process, sterilization process, is with dosimetry mainly, knowing that before doing the process, there is a lot of work to be done in terms of microbiology, definition of the sterilization dose, max acceptable dose, as I already mentioned, and more than this, a lot of work to be done for the qualification of the irradiation plants. The future of dosimetry is maybe not longer those measurements. It might be something dealing with simulation. And here I have some examples of a product being irradiated with a 10 MeV electron beam, where you can see zones, the blue zones and red zones of minimum dose and maximum dose given to this product after 10 MeV irradiation. This also, these tools which are coming and which are more and more simple to be used, will also help to define what we call the a potential parametric release, using less dosimeters, more simulation, more process control and process parameter controls, leading to less usage of dosimetry. And this, I think, will come in the next 5 years or 10 years. So this is it already. This was a short introduction on the technologies which are used.
Merci bien, Florent, pour l'introduction. Thank you so much for your remarks, and stay tuned. Stay with us, please, because we need you for the in short following discussion. So stay with us. Second little intro speech we will have with Martin Comben. He is with us as a member of the IAA team, supports the radiation processing industry and promotes the safe, beneficial use of irradiation. Previously, he worked for over 20 years in various international business roles where he developed his extensive knowledge of the irradiation market technologies and the operational and regulatory environment. Before you start, Martin, I hope you are with us because I can see you right now. I guess that I have to point you, dear participants, to the knob, the form where you can ask your questions that we will address in the following discussion. But for now, Martin Comben, opening remarks by you, please.
Yeah, thank you, Andreas, for the nice introduction. Can everybody see my screen and hear me?
Yes, we can see it. It's not the full screen yet, but you'll get there in a second, I guess.
Okay now?
Yep, wonderful.
I can see the screen, Martin.
Yeah, okay, thank you, Florent. Okay, so let's start. So, yeah, thank you for the nice introduction, Andreas. As Andreas said, I'm General Manager of Gamma Irradiation at the International Irradiation Association, and we represent the radiation processing industry. We are technology neutral, so we advocate and support gamma, E-beam, and X-ray technology and applications. And And today I'm going to just introduce you to the market and the industry, give you a little introduction to some of the issues and the challenges that we're facing, and give you an indication of the direction of our industry and how it may look and how it may evolve in the future. So just to give some perspective, the global medical device sterilization industry is forecast to be valued at about 7 million euros by next year, with an average global growth rate of about 8%. This translates to about 12 million cubic meters of medical devices that require sterilization within Europe by various technologies. And you can see on the chart at the bottom of the screen how these technologies are shared. So about half of the product is treated with ethylene oxide gas. About 40% market share is held by gamma using radioactive cobalt-60, and about 10% is the other technologies, so E-beam and X-ray. X-ray today is maybe 1%, perhaps even less, with E-beam being the majority of the rest. And of course, there's some global some regional variation. So in some regions, for example, E-beam may be higher, perhaps 15%, and ethylene oxide may be a bit lower. But broadly, it's about this picture. And I think what we're going to see in the future is that the technologies in the other section, what is shown at 10%, this is the area where we're going to see growth. So E-beam and X-ray are going to start growing and taking market share from the other technologies. And that's a good thing. It means that our industry has options. It means there's a bit of competition between the technologies. And most importantly, it means that our industry will be able to continue meeting the sterilization demands of the medical device industry. And that's really important because today there is some global constraints on sterilization capacity. And it's impacting both in-house operators and the companies that are offering contract irradiation or other sterilization services. And it's down to two key issues that relate to ethylene oxide and gamma. And remember, ETO and gamma, they are used for sterilizing about 85-90% of medical devices globally. So it's important. I'll just touch on the reasons. With ethylene oxide, there's over the last probably 2 years, there's been increasing concern about ethylene oxide emissions from these ETO sterilization facilities. There's increasing regulatory pressure, particularly in the US, and that's resulted in the closure of some facilities, to the point where the FDA issued this statement, I think it's about 18 months ago now, but highlighting their concern with the availability of medical devices due to the closure of certain ETO facilities. And this statement was made when there was a discussion about closure of 4 facilities in the US. So 2 were in-house, 2 were contract facilities. And it really highlights how closely matched supply and demand is. You know, the closure of 4 facilities is causing the FDA to issue these statements. And it's not 4 companies, it's just 4 facilities. So that's the situation with ETO. With gamma, it's about a tightness in the supply of cobalt-60. And I think most of you will be aware that cobalt-60 is the radioactive material that's produced in nuclear reactors. It produces the gamma radiation. So it's like the fuel within inside the irradiator. And the less cobalt you have, the less product you can sterilize. And there's a number of reasons. I won't go into too much detail, but of course, some of it is on the demand side. So the demand for cobalt and the demand for gamma irradiation is high as it's ever been. So some of it is on the demand side, but also the supply side. So there's a number of elements, but one of the elements is that a state operator of reactors made the decision to reduce the amount of cobalt that they were producing. There's also a number of reactors are going through refurbishment and maintenance. And that's important because it after refurbishment, a reactor typically can operate again for 25 or 30 years and produce cobalt for 25, 30 more years. But during the refurbishment process, the reactor has to close down for 3, 4, 5 years, depending on the work that's being done. And of course, industry is working really hard behind the scenes to try and address this tightness. The suppliers and the reactor operators are trying to bring forward these refurbishment programs, transfer production of cobalt to other reactors, introduce new technology so different types of reactors can produce cobalt and so on. So there's a lot of work being done behind the scenes. But it is these two issues, the constraints with ethylene oxide and gamma, that are driving the demand for different technologies. And it's what's causing our industry to evolve. So if I just talk to you a little bit about the status of the industries today, and then we'll talk about the future. So for gamma, it's a very well-established, it's a mature industry. It has a very robust infrastructure. There's a large number of irradiators meeting the global demand. There's a well-established regulatory infrastructure. And of course, there's a huge number of medical devices are approved for sterilization using gamma. The challenge, it's all around the availability of cobalt-60. We need to try and increase production in order to match the increase in demand. With E-beam, of course, it's also really well established. The technology is in fact, the E-beam irradiation for cross-linking of wires and cables and for material modification, it's the largest industrial application of irradiation in the world. So even larger than medical device sterilization. So there's no doubt that the machines and the international infrastructure is there. The challenge is perhaps maybe finding ways of moving medical device sterilization to E-beam technology in order to meet demand. And there's been some discussion previously about the challenge, and that is that E-beam is a low penetration technology, so it's good for surface treatment and maybe low density products. But the challenge is finding ways of getting the sterilization dose to the product. And then with X-ray, this is the newer emerging technology. There's a lot of interest. There's a lot of momentum, motivation, and investment has started in X-ray technology. And there's a number of challenges, but in very general terms, there needs to be a good understanding of how the X-ray is going to impact the material and the products that are treated. So lots of mechanical testing and functionality testing of products and so on. Those products then need to be approved by regulators for sterilization with X-ray. And also the infrastructure needs to develop. The number of X-ray machines around the world is very small, and it needs to grow in order to meet the global requirements of the medical device industry. It will come, but it's not there yet. So for the future, I think we're going to see that all of the sterilization technologies are going to continue to grow, not just irradiation, but ETO and other technologies as well. Gamma, it's well placed. It's got there's a big infrastructure with large volumes of product approved for treatment with gamma, so it will continue. It is really only limited by the availability of cobalt-60. I think with E-beam, the volumes will continue to grow and new applications will be found, maybe at a smaller growth rate, and it may be limited to certain products. And I'm sure a lot of clever work is being done to to get the dose to the product, maybe through different package types and so on. And with X-ray, it's going to continue to develop, and it will emerge as a more routine technology for the sterilization of bulk medical devices. We've already seen investment start. That will continue, and it will continue to take market share. And it may look something like this. So you'll remember the chart on the left, which is the market share by technology today. The chart on the right gives an indication of how it may look in, I've dated it 2035, it might be 2030, who knows, but it's for indication only, really. So this chart, I think there's 3 points that this highlights. One is, of course, that the global market has grown. We talked, remember, earlier about 8% a year. The other big change is that the other section, the accelerator, the machine-based irradiation technologies have grown and taken market share from the other technologies. The biggest change is X-ray. Remember at the beginning I said maybe 1% or less volume is treated with X-ray. We're going to see that grow for sure. But the third point that this illustrates is how gamma irradiation continues to be really important and remains the cornerstone of radiation sterilization. I think there'll be some other changes. We may see some of the larger medical device companies moving sterilization in-house. I say this because at a time of risk, and there is a risk today that not all of medical device sterilization needs will be met. And at time of risk, the medical device companies may choose to take control of the process and move it in-house. I don't think that'll happen with gamma, but it may happen with the accelerator, the machine-based irradiation technologies. So I hope I've been able to show you that our industry is continuing to evolve in order to meet sterilization capacity, but also to assure you that all technology is going to remain critical if we're going to meet industry's demand. Thank you very much.
Thank you so much, Martin, for your insight and for covering all the fields of sterilization for us, and good grounds for our discussion that will follow right now with 3 partners, because along with Florent and Martin, Dr. Andreas Ostrowicki is again with us, managing partner of BGS. He joins us for the discussion, and if we looked at the pie that Martin just showed us, it's pretty encouraging for you, I think, because gamma pretty much stays where it is right now in 2035 in his projection, right?
Yeah, I think absolutely. It's a more diversification, I think, of technology that we see growth also in other areas. And I think we have a common opinion here that in this industry there will be strong growth. Mm-hmm. And of course the question is, nobody knows if it will be into the direction of X-ray. I mean, we have certain concerns about that technology. It solves certain technical questions, of course, mm-hmm. but the economics and also some parts of the validation process, they have some questions still to solve. So, but I think the message is positive that we expect that growth and that we see. I fully agree with Martin here, mm-hmm. that we probably have the workhorses, cobalt and ethylene oxide here to deal with the large part of the volumes.
I think for the time remaining for our discussion, I would like to point again to cobalt, what is solvable there. I would like to point to X-ray a little bit, but first of all, I'd like to involve Florent again in Strasbourg, if he really shares what Martin just showed us, the overall growth in all segments, in all methods we are facing, that basically every technology is going to grow. Do you share this?
Yes, absolutely. The last slide is kind of a risk Martin took, but I think it's probably a a good estimate. What we can see here at IRIA, we have more and more companies coming to us and willing to test their products for electron beam or X-rays. And I have to say that today more and more are coming with products they want to irradiate with X-rays. So the big development is probably X-ray today. And my position to that is probably the fact is that X-ray is a photon, as you know, and it's probably something people understand being something equivalent to cobalt-60, equivalent to the photon of cobalt-60, which is correct. So it's a kind of one-to-one conversion,
right?
Almost, which makes it easier. But as I already said, electron beam is a technology which is, in terms of energy, more efficient. So the trend, and Martin pointed out that E-beam will be also gaining in terms of volume and power installed. Trend is probably in the next years, more installations, more medical devices being sterilized with electron beams.
Yeah. Thank you very much for your input. And I would like to ask in general, if we don't have a regulatory framework for X-ray, if we have, as Martin pointed out, a knowledge gap in there, if we don't have product approval, why on earth should we go down this path? Do we really need it, or could we have more extensive use of the technologies that are in place, Martin?
Yeah, it's a good point, and it's encouraging that we're seeing the investment in X-ray and being made at the same time as the filling this knowledge gap and getting the regulatory approvals to use X-ray, because it would be tempting for nobody to invest until the product is ready, but equally it would also be tempting for people not to get their product approved for treatment by X-ray if the infrastructure is ready. What we're seeing, which I think is encouraging, is that both are growing. Both those investments are being made at the same time. I wanted just to make one point also. I wanted to add just about something that Florent said, was that about we are going to see a change in the use of technologies. Gamma is going to remain critical. And I think it's really important for companies to maintain their gamma approvals and their qualifications. So even if they're considering moving to a different technology, they should maintain the gamma qualification. Mm-hmm. It'll give them business continuity, and it will give them flexibility and a choice of technologies to use, mm-hmm. which is important if there's constraints in capacity.
I guess that Andreas would not challenge this to keep up with gamma capacities at BGS, right?
Yeah, absolutely. And I mean, if you talk about X-ray, and I liked Florent's statement, a photon is a photon here, but it is not exactly that. I think we should also keep that in mind. I mean, the gamma radiation we have from cobalt has a quite different spectral property. It's a single energy line what we have here, whereas with the X-ray we have a broad energy range. What gives us some issues here also. There is a lot of question about will there be activation of products? So does this radiation actually make certain products radioactive? That is one big issue what has to be clarified. And for us, I think the even bigger topic is the energy efficiency of that process. If you consider that with an X-ray machine we have something in the range well below 10% conversion of energy into radiation, we are quite concerned about the cost impact. If you consider high energy prices here in Europe, especially in Germany. So we would estimate it is certainly not a cheaper alternative to cobalt. Yeah, and also the impact, as long as we have fossil production of electricity, it will have a big impact on the climate gases. And so that keeps how to say, this keeps us a little bit skeptical if this is really if it has that potential to develop, as we think it is more an intermediate technology. And certainly not the best possible solution. If you compare to electron beam, of course, a completely different matter with penetration, as we don't have this deep penetration. But the really big difference here is that we have a much better energy utilization of that process. And that fits, in our belief, a bit more in these times where we have also to consider these effects.
Absolutely. Martin and Florent, in answering this, maybe we call it the X-ray craze, so to speak, have something to do that, I mean, if you don't like EO and you don't like gamma at the same time, you're kind of, in severe problems. So you have to define an escape path, sort of, right? Martin, maybe you first.
Yeah, unfortunately, we lost Andreas a little bit then, but you were talking about the green credentials, I think, of the various technologies. I'm sorry, it was cut out a little bit. And it's a real, I don't think there's a clear answer. I mean, if you think of cobalt-60, of course you have radioactive material, and our industry has done an outstanding job of recycling radioactive material, but ultimately it will become radioactive waste. And then, okay, so you look at E-beam, and to a greater extent X-ray, it relies on electricity. And where does that electricity come from? It comes from power stations, and then maybe your view is determined by where you are. So in Germany, it's, I think, less than 10% nuclear power. So you may have a different opinion to somebody in France, where there's 70% nuclear power. Right. And then it's whether you agree with the sort of clean air argument of nuclear. So I don't think there's a clear answer, and I think it's like everything. You can make an argument for any technology.
Right. Florent, your take. I mean, Germany is going to zero in nuclear power. So this is define the path forward. So this is pretty clear that we're going to stick to this. Quite frankly, in the opposite direction of what's happening across the Rhine River, Florent.
Yeah. Exactly. In France, we have more than 70% nuclear power, and today I really agree with Andreas. X-ray is for me a transition technology, and the problem we face is multifactorial. But I think Today, we cannot only decide about one or the other technology only with the economical aspect. I think we have to take the ecology and the green aspect of the technology into the calculations. And then something I recall from your last comment, Andreas, you said you are not willing to use EO or willing to use gamma, or you are not accepting. But it's not a question of accepting or willing. Some of the medical devices cannot be radiation sterilized today. They have to go through EO because there are a lot of material properties which are impacted by the radiation, and there is a huge job to do with the medical device industry to adapt the materials to be able to be irradiated. Because irradiation is a more safe technology, There is parametric release, no microbiology test and sterility test after the irradiation. There are many standards. It's a well regulated technology. I think the medical device manufacturer have to be a little bit more proactive, I would say, to do this transition to radiation sterilization and more to E-beam sterilization.
Very interesting point. I'd like to give it over to Andreas at this point and add to this what can the industry, the medical device industry, by themselves do to have a more consistent and a more organized kind of acting together with all technologies and the actual manufacturers of medical devices?
Yeah, I think we had the point earlier today already. I think it has a lot to do with working proactively on certain topics here. That what we see a lot is now that people come and say, look, we are sterilizing this product now by gamma radiation, and we would like to transfer it into E-beam sterilization. And then we see the case that in principle the product would be capable, let's assume with some kind of plastic, some device made of plastic, so density, all that would fit, but the packaging schemes don't fit, and that blocks the whole project. So you would basically have to repackage the whole thing, start of course all the validation steps. There's a big transformation then linked to that. And so this comes to the point of strategy, that you should be clear in an early phase what you're planning to do here. Once the conditions are set, it's extremely difficult to get out of this border.
Very interesting. I will not forget to pose some questions by the audience. One, Martin, I would like to give over because it addresses X-ray, and the listener wants to know, technology-wise, X-ray is superior over E-beam. We might discuss that in itself if we want to. However, can E-beam be used as a bridge as X-ray capacity builds up? Your take.
So I think X-ray certainly does have some. There are indications that X-ray has some technical advantages, in particular lower overdose over gamma. But broadly, as Florent said, I think they are seen as being broadly equivalent. If you're going to use E-beam as a stepping stone, I'm not sure of the regulatory requirements here. Certainly, you could. If you can address the technical challenges of getting the dose to product by E-beam and get your product approved for treatment by E-beam, that would be a really good positive step. But then it's another big step to getting the product reapproved for treatment by X-ray. So what is approved for X-ray is not necessarily, what is approved for E-beam is not necessarily approved by X-ray. Whilst they're both technologies that use accelerator machines, actually the irradiation is quite different.
Thank you, Martin.
I'm sure they have an opinion on this also.
Yeah, I can comment on this question as well. In terms of regulation aspects, of course, a dose is a dose when it comes to sterilization. But having a radiation field which is different between X-ray and E-beam, and especially dose rates, there are some oxidative effects on polymers, which lead to probably a different maximum acceptable dose for the medical device treated with E-beam. So on the lower side for sterilization, a dose is a dose, but at the higher dose for the maximum acceptable dose, it is not equivalent. And it might be equivalent, but it has to be determined, it has to be assessed. So a switch from one modality to another one needs work. What I wanted to add for the switch to E-beam, it needs more knowledge, more experience, because E-beam, as I already said, is a charged particle. There is a mass. The dose gradients inside the boxes of devices are much bigger than for X-rays or gamma, which could lead to higher DURs, higher dose ratios. And this has to be really assessed by the sterilization contractor. So it needs knowledge and specific competencies when you go towards electron beam, more than changing from gamma to X-rays.
Thank you, Florent and Martin, for your in-depth answers. And we learned that the word bridge technology gets a very different sound when it comes to E-beam as a transitional force to X-ray, which it might, after all, not become. We have one question for Andreas. How do you think, Mr. Ostrowicki, about X-ray in general? Because energy will be green soon in Germany, and the overall efficiency of X-ray is, in the eyes of our participant, not that bad or considered.
Let me answer this. So first of all, I think we have clearly different technologies here. Yeah? X-ray comes most close to gamma, but it's not exactly the same. And that is the one thing. And if you consider the question of energy supply, I mean, if we look at the situation, we will have an awful lot of industries converting into electrical energy in the future. I think this argument that we will have a surplus of electricity here in the coming years is not really realistic. If you consider all the cars being transferred, the different industries, I think we could well see that we will have still a shortage and quite high prices of electricity, and that will be still an important factor here in this. So I think it is the technology which is able to, to compensate most closely to the gamma technology compared to other technologies. It's not the same, but we expect definitely it is not a cheaper solution. Right. That if you look at efficiency and cost, where possible, we would recommend really to deal here with E-beam.
Okay, understood. One question, Martin, that might or might not sound a little exotic comes from our audience. And I mean, we're talking strictly medical devices, and this question touches on food. How do you think about irradiation of food products in the future, especially in Europe? Any thoughts?
Sure, I have some thoughts. I think food irradiation is quite well developed in some regions of the world, not just for extending shelf life and for improving the quality of the food, but also as a phytosanitary treatment. So, for example, a lot of fruit product is exported from Southeast Asia and Australia and Latin America to the US, and is treated with irradiation for phytosanitary purposes. Phytosanitary being that is the process of ensuring that the product arrives at its destination in a clean condition, and it's a great alternative for a gas treatment. For Europe, I'm not optimistic, to be honest. I know that people have been discussing the potential of food irradiation in Europe for as long as I can remember, probably 30 years. And whilst the technology it's accepted that the technology works, and the technology is there and ready to go, but the regulatory, there's two things. There's market acceptance, and I think we're seeing an increasing market acceptance outside of Europe, where irradiated product is available. And, many companies used to say, we're not going to be the first company to start selling irradiated food. Now that's not happening so much because there is increased acceptance. But in Europe, it's a regulatory hurdle. And I'm not very clear on the details, but my understanding is that within the European Union, you have a list of foods that can be treated. And that list is submitted to every member state of the European Union. And if one country doesn't like one food on that list, then the whole list has to be rewritten and reapproved. So at the moment, the volumes are very low, and I wouldn't be optimistic about the adoption of food irradiation in Europe.
Who knows? Maybe.
Here as well.
Florent, please.
Okay. Well, I'm not completely. I do not completely agree with you, Martin. Yes, the regulatory aspect in Europe is a clear hinders the development of food irradiation. But I think some producers, you mentioned phytosanitary application. This is a really, really great application when it comes to food. We don't want to have in Europe products, potatoes irradiated or ground beef irradiated. We don't need this kind of foods being irradiated. But what we need, because there is a lot of industrials mixing spices, dry herbs, etc., for preparing dishes, etc., they are really, really interested in spice irradiation, herbs, aromatic herbs irradiation, because it is a very good and efficient technology and it doesn't use gases. But here, yes, there is a regulatory problem, but the regulatory problem can change if the producers of these peppercorns or whatever open the door of the EU and or at least knock on the door of the EU, work together with the retailers to accept the treatment of this kind of products, because the consumer does accept, I think, irradiation when it's when he is well informed. So the food irradiation in Europe is very, very low, as you said, but I hope that in the next years, at least decontamination, radiation decontamination of spices, herbs, aromatic products will be accepted.
Thank you so much for your input. And who knows, maybe even the Corona crisis pays into this, that general publics also in Europe say, okay, maybe there's some good, even though it's irradiation, in this process. Andreas wanted to add something to the food topic as well.
I would also like a little bit to share our view here as a service provider. And I must say, I'm much less enthusiastic about this. Because I think, first of all, we have to look in the EU. We have now a food irradiation of about, I think, 5,000 tons a year. Worldwide, we talk about 500,000 tons going upward. And first of all, I think there is not really a need, unless we have specialties like Florent mentioned, very herbs and spices, certain areas where you have no alternative really. But I think it comes mostly in place where you have countries, very big, very long transportation routes, hot, humid climates, and that makes sense. And I mean, we should not forget, we are talking about a shortage of cobalt here. And I would question, does it make really sense to use more cobalt for food irradiation? Okay. As long as we have here good logistic chains, good cooling chains, everything in place. There's not really, I don't see really a dramatic need for that.
Mm-hmm. Mm-hmm. Very interesting point, Andreas. Gentlemen, we are coming slowly but surely to the end of this very fruitful discussion. I would like to stay with you for another hour, but we didn't schedule that because we have so many topics left over. Andreas just mentioned one, which is the cobalt topic. And once more, I'd like to turn it over to Martin with that point. We are talking constantly about the cobalt-60 lack that we are facing right now, or at least the tightness in the supply. Why can't we think about or put in place something that would increase the production, maybe even in Europe? Or is that kind of a fairy tale?
Yeah, I think the phrase I used was we can't turn the tap up and just more cobalt pours out. I think there are a number of barriers to cobalt production, and I can give you a bit more detail. If you start at the production end, cobalt-60 is produced in nuclear reactors. The core operation of a nuclear reactor is to produce electricity. So first of all, you need to justify producing cobalt, and there's a perceived risk if you're going to modify a reactor. And start producing cobalt, even if it's a well-established conversion process. So first of all, you need to justify it to the reactor operators. They will have a risk-reward process that they go through and determine whether it's acceptable to them. Then there's regulatory requirements and so on. If you go through all of that, then you have to, you can produce some cobalt. But then you have to take that cobalt raw material and manufacture it into a product that's usable in the industrial irradiators. And that in itself is a big hurdle. The handling of radioactive material requires very specialist equipment. The manufacture of the sources needs hot cell facilities and lots of specialist expertise. The product needs to be tested and licensed. You then need special transport containers for transporting the material from the reactor to the manufacturing site, and then from the manufacturing site to the user. Again, they need to be tested and approved. So it's a big investment. You mentioned Europe. You're right. There's no cobalt-60 production in Europe. There is discussion with a reactor in Romania. Nordion, the largest cobalt supplier in the world, is in initial discussions with the Cernavodă reactor in Romania. That could, in the future, add to the production of cobalt-60. Unfortunately, it's not going to add to the competitive environment. It's just going to mean that there's more cobalt available. It's most likely that cobalt would go through to Nordion, who would then introduce it into their manufacturing chain and so on. Mm-hmm. So there's a number of challenges, and it's a huge investment, both in terms of regulatory requirements and physical assets that are needed. Mm-hmm. So yeah, I hope that answers your question. Mm-hmm.
Thank you for this in-depth answer. We might put it in a nutshell. It's not going to happen. Maybe this would be appropriate, at least at this point in time. So we're running out of time. I have one more from our audience, which is very simple. Andreas, probably you can say something to that. Is there any material database available for materials which can be treated with E-beam? Okay. Is there any material database available for materials which can be treated with E-beam?
Yes, very, very simple answer. We have a lot of knowledge on that and we can advise, but it is a very specific topic and we would like to answer this in detail. Maybe I would like to add just one sentence to your former closing. I think it's not clear it will not happen, but it will for sure. If it should get some momentum, it will take a long time. I think I fully agree with Martin. It's very complicated technically and from the regulatory point, and of course depends also on the political will. But the question is, what alternatives do we have?
Yeah.
How do we want to solve that issue? That is the
exactly. So my nutshell version was not quite accurate. I get that. That's okay.
I agree.
No, yeah.
Martin is nodding, which is very good. Thank you, gentlemen. Martin Comben, International Irradiation Association, Florent Kuntz, Ariel, and Dr. Andreas Ostrowicki, BGS, our host for our fair. This was a very interesting round, very interesting discussion, and plus presentations. I enjoyed that big time. Thank you, ladies and gentlemen, for your questions you put in. I hope we could answer it kind of, or get in touch with us if you want further interesting discussions with our speakers. That will be possible on our platform anytime. Thank you again.